Let's consider one last example. Here we'll start with a random variable x that has a normal distribution with mean mu and variance equal to 1. And suppose we define our hypotheses to be as follows. The null hypothesis states that mu is equal to some mu naught, which is just a number, versus the alternative that mu is equal to mu 1, which is strictly less than mu naught. In the first part of this problem, we want to find a value k so that x bar minus k provides a rejection region of size alpha equal to 0.025 for a random sample of size n. Now remember, alpha is our probability of a type 1 error. So we're looking for the probability that x bar is in the rejection region, so it's less than k, given that mu is equal to mu naught, which is the value of the mean given in our null hypothesis. So if we use the methods that we've learned previously throughout the semester, we can standardize this x bar variable to produce an equivalent probability statement. We're looking for the probability that z is less than k minus mu naught divided by 1 over root n. And if you're wondering where these values come from in this standardized version of our x bar, remember the mean is given by our null hypothesis, so we're subtracting the mean, and we should be dividing by the standard deviation of the x bar variable, and from theorem 8.1 we know the standard deviation of the x bar variable would be the standard deviation for the original variable divided by the square root of the sample size. And since the variance for the original variable was 1, then the standard deviation is as well. Now let's just take a step back for a moment and try to put this in perspective. I've got this normally distributed random variable, and my goal here is to find a value k, so if I chop off area in a tail, the area of that tail is equal to alpha, which is my probability of a type 1 error. And how do I know that this is a left tail that I'm chopping it off? Well, my rejection region looks like it's representing something that's a left-tailed region. Alright, so if I think about what this means then, this value k minus mu naught over 1 divided by root n represents the equivalent z-score if I were to rescale this to the standard normal distribution where the center would be at 0. So I'm looking for a z-score then that has an area of 0.025 in the tail, and it needs to be a negative z-score. Referring to a z-table gives us the z-score with an area of 0.025 in the left tail. That's a negative 1.96. So set that equal to k minus mu naught over 1 divided by root n and solve for k gives that k is equal to mu naught minus 1.96 divided by root n. Now let's move on to part B. Here we're interested in determining the minimum sample size needed to test the null hypothesis that mu is equal to 7 minus the alternative that mu is equal to 6.5 with a probability of a type 2 error being less than 0.04. So let's just take a step back here for a moment and put this all back into perspective. We started with a normally distributed random variable centered over mu naught because that was the hypothesized mean for the distribution. We found a cutoff value for k so that the area in the left tail corresponded to alpha, our 0.024. But now in this problem, we're looking to write a probability statement that involves the probability of a type 2 error being less than 0.04. And remember, in the previous example, when we were finding the probability of a type 2 error, we were looking for a probability based upon knowing that our random variable was not in the rejection region and we had a different true value for our parameter. In this case, that true value will be the 6.5. In other words, we have to take our normal distribution and shift it to the left because the alternative gives us a mean that's strictly less than our hypothesized mean from the null hypothesis. So then we want to use that same k value, but now when we're chopping off area in the tail, things that are less than k, remember, corresponded to the rejection region for our first distribution. Things that are greater than k correspond to the not in the rejection region. So now we're looking at the area in this right tail. We want this area to be less than 0.04, and we want to put all of this together. In particular, let's first think about what k is. Using part A, we can then say that if our null hypothesized value for mu is 7, that k should then be 7 minus 1.96 over root n. And for a probability for a type 2 error, beta is the probability that x bar is not in the rejection region, so it's strictly greater than k, given that mu is given by the alternative hypothesis equal to 6.5. So we'll replace k here with the value that we've computed based upon part A, and then we will then take this expression the probability that x bar is greater than 7 minus 1.96 over root n, given that mu is 6.5, and we'll standardize again to compute z-scores, so we'll subtract the mean. Now the mean value is taken from the alternative hypothesis, and we'll divide by 1 over root n, and we'll get an expression that says that beta is equal to the probability that z is greater than the square root of n over 2 minus 1.96. Now keep in mind, this means that we're looking for a z-score where the area in the tail beyond that z-score is 0.04 or less. Referring to a z-table, we find that z-score is equal to 1.75. We'll set that equal to the square root of n over 2 minus 1.96, solve for n, and we'll get 55.0564. Now it's worth noting here that n is supposed to be a sample size, and it doesn't make sense for it to be fractional or decimal. As such, we're going to round up to the nearest whole number. So we'll pick n to equal 56. Now this concludes our discussion of Chapter 12, and when we move into Chapter 13, we'll be discussing more formally the various steps involved in a hypothesis test, as well as looking at specific examples from start to finish. Thank you.